All right, welcome to lecture 6.3. This is the last lecture in the series. This one involves polar coordinates. So we'll go ahead and look at the section objectives and then we'll get moving forward here. Okay, so the objectives for this particular section are, we're going to learn how to plot a polar coordinate. We'll actually have to find out what a polar coordinate is. And we'll have multiple sets of polar coordinates for any given point in the Cartesian plane. We'll convert between polar and rectangular coordinates are just the good old XY coordinates that you're used to seeing. So we decipher between these two by saying polar, and you'll see what that is in a moment. It's got a circular graph, and then rectangular for the good old XY plane. And we'll convert back the opposite way. We will take an equation from rectangular to polar, and then we'll flip-flop that and go from polar to rectangular with an entire equation. All right, so if you're following along with your note sheets, we have a couple blanks to fill in, and I like to use blanks when we have definitions. It makes it seem a little less cumbersome than just writing out definitions. So, the foundation of the polar coordinate system, I didn't put your first blanks on the page. I forgot to insert a butterfly slide here, so if you're following along on your notes, you have the pictures of the butterflies with the polar coordinate butterfly, or the polar graph of the butterfly there, and it says butterflies are among the most celebrated of all insects. It is, sorry, my brother's calling. It's not hard to notice their beautiful colors and graceful flight. Their symmetry can be explored with trigonometric functions and a system for plotting points called the polar coordinate system. Those are the blanks on that first page. So believe it or not, in many cases it's actually simpler to use polar coordinates than it is rectangular coordinates. So the foundation for this system is a horizontal ray that extends to the right. The ray that we start with is called the polar axis. And then the end point of the ray is called the pole. And so the points P in the polar coordinate system come in the form of r theta. So we know r from our unit circle as the radius, which is also the hypotenuse of that right triangle that gets formed. So if you look here, you could, at this diagram down at the bottom, you could imagine a circle coming through, and use your imagination on my circle. It looks more like a blob. So you can imagine that radius being from the center out to that circle, and then if you dropped that plumb line down, you'd have the right triangle that we base our knowledge of the unit circle off of. So all the points in the polar coordinate system come in the form of r theta. We define r as the directed distance from the pole, so that's the terminal end of the polar axis, all the way out to whatever point we're trying to work with. And then theta, of course, is the angle from the polar axis to R, basically, to that terminal side. Angle can be measured in degrees or radians, so you'll want to be careful if you're using your calculator to make sure that it's set to the proper mode for whatever problem you're working. Negative angle, so this is all old hat type of information for us. A positive angle is measured in the counterclockwise direction, and a negative angle is measured in the clockwise direction. Okay, so if we simply want to graph a point, and these are pretty cool looking graphs, aren't they? I think they're cool looking. Of course, you know, that's in Ms. Gore's nerdy world, that stuff like this is cool. So we have a given point, and I've got my, let me move my board over here a little bit so I can see, 315 degrees. So our R is 3, or the distance from the pole of the polar axis, which would be the center of our circle. The distance from the center of the circle to the point is 3, and then we want to place it positive 315 degrees around the circle from the polar axis. So the first thing I'm going to mark is the polar axis. We have the pole at the center of the circle, and the polar axis is always that horizontal ray to the right. So it's the very position that we're used to starting our angles in, even in the rectangular coordinate system. All right, so we want to start at the polar axis, and we want to move around the circle 315 degrees. And so that's going to be halfway between 310 and 320, which is about right there. And we need to put the point a length of 3 away from the center. So our point ends up living about right, let's see, 1, 2, 3, and it's halfway between 310 and 320 degrees, so about right here. That's the point P, which is 315 degrees. Okay, so let me do a quick check of y'all and see that that made sense, that y'all followed everything. So just give me a green check if you're good to go, or give me a red X if you have a question. Jessica says she's great, and Josh says he's great, so I'll go ahead and clear those out and we'll move forward. Okay, so now we're going to see, okay, so what the heck does it mean to be a distance of -2 from the pole, or the center of this grid here? And what it means is you're going to go ahead and move around the circle. In this case, we're going to move 3 pi over 2. So now notice I gave us a grid that's scaled in radians, so we don't have to rack our brains to think about the unit circle as to where 3 pi over 2 is going to be. You'll move 3 pi over 2 around the circle, and instead of putting your point actually, let me go ahead and get that drawn. So first we have our polar axis. There's our center or our pole, and there's our polar axis. 3 pi over 2 is 3/4 of the way through the circle. So I'm going to go ahead and mark that. So we start at the polar axis and we're going to move all the way around to 3 pi over 2. Now, if our R coordinate were positive, we'd simply put a point right there on the second unit out from the center, and we'd be done. But it's a -2, and so what that tells us to do is move 2 units directly across from where it would have landed. So our point P actually lives right there. So we're still 2 units from the circle, or from the center. We're just on the opposite side since our R value is negative. So this is point P right here that's -2, 3 pi over 2. All right, give me an indication as to how that was for you. Green check or a red X? Green check, yay! Okay, same thing here, but notice this time not only is R negative, but I also have negative theta. And the only difference with this is when we move theta, we're going to be moving in the clockwise direction this time, since it's a negative angle. So here is my polar axis. And I'm going to move -pi over 2, which is 1/4 of the way through the circle. So I start at the polar axis, and I'm going to move -pi over 2, which puts me right there at -3 pi over 2. So if my R coordinate were positive, it would sit 1 unit away, but since it's negative, I've got to cross over. And so my point P lives right there. So that's -1, -pi over 2. Y'all ready to move forward? Don't be bashful if you have questions. Okay, so now here's a little bit different type of problem. We're given the polar point here, 5 pi over 4, and we are asked to find some other representation of that same point that lives between 2 pi and 4 pi. So let's take a moment to think about this. 2 pi is 1 full circle. 4 pi is 2 full circles. So say I have some arbitrary point hanging out here. And let me give, oh God, that was awful. That was supposed to be a vertical line. Goodness. I've been up since 4 a.m. That's my excuse, at least. I've been working since 4 a.m. All right, so let's say that point lives there in the rectangular coordinate system, and we want to move through. I can hit that same exact point going another 2 pi around the circle, or another 4 pi around the circle. So we're looking for a point that lives at the same location but has a different r or theta. Well, it's not going to have a different, well, it could have a different r just depending on how you look at it. It could be the -5, but a different theta coordinate. Okay, so let me erase all this business over here because I need a little bit of room to work. All right, let me get my black pen too. Okay, so we start out with the point 5 pi over 4. And which, just for the sake of thinking about it, puts us right here. Let's see, 1, 2, 3, 4, 5. Yeah, so that's 5 pi over 4 right there. If I add 2 pi to that, that's going to be 2 pi plus pi over 4, which is going to live between 2 pi and 4 pi. So that's exactly what I'm going to do, is just add one full rotation to, I'm going to add one full rotation to my theta coordinate. So this is 5, and then I have pi over 4 plus 2 pi, which, once again, if I start at pi over 4 here, it's going to land me right back at that same point. So all I need to do is a little bit of a fractional addition there. So I've still got my coordinate 5, and then pi over 4 plus 2 pi over 1. Well, I need to get a common denominator to be able to add those, so I need to multiply 2 pi by my clever form of 1, 4 over 4, to get a 4 in the denominator. And now I have 5 pi over 4 plus 8 pi over 4, which is 9 pi over 4. So if I move 9 pi over 4 and stay on that that circle that's 5 units away from the center, I'll just show you what that looks like. So we have, there's pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, 8 pi over 4, so that's 2 pi that I've gone back through, but I have that extra pi over 4 that I began with. So 9 pi over 4 takes me right back to where I started. If I begin counting the 9 pi over 4 from the polar axis. Was that one okay? Did y'all understand that one? And I see Jessica has a little bit of lag on her audio, so we'll give her a second to catch up with us. Okay, great. All right, so same point, except this time we're told, okay, find another representation of that point, but this time we want r to be negative, and we want theta to live between 0 and 2 pi. So we want our theta coordinate to live within a single rotation through the plane there. All right, so this is what we need to do. Now, we would start, if the point were just what we started with, once again, we're here. So if I make 5 negative, if I make my R coordinate negative, that puts me directly across at 5 pi over 4 there. So if I make, if I can send, let's see if I can explain this okay. If I can send this point pi through the plane, so if I add 1 pi, that's going to land me here, and then making the point negative is going to send me back across to land me back where I started from. So all I have to do with this is negate my R coordinate and add pi to my theta coordinate. This is what that would look like. I start out with 5 pi over 4, and I'm saying that is equal to, let me get a different color to point this out, negative 5, and then pi over 4 plus pi, so I have to do some fractional math again, negative 5 pi over 4 plus, well, let me not take up too much room here. I need to multiply that pi by 4 over 4 so that I have 4 in the denominator, which gives me 4 pi over 4. So the coordinates would be negative 5 and 5 pi over 4. Now let's test our theory by just graphing our new point. So I'm going to take all this off the graph. Okay, so if we move, let me draw my polar axis again. So here's my polar axis. And if I move 5 pi over 4 through the plane here, that puts me right there. And I want to move 5 units out from the center, 1, 2, 3, 4, 5, right here, except my point is negative, or my R coordinate's negative. That's going to shoot me all the way across. And I'll land exactly where I would land if I had the point 5 and pi over 4. Was that super confusing, or are y'all cool with that? You have to be a little bit clever when you think about these. Okay, great. So it wasn't super confusing. Bonus. Okay, and our last example here says, find another representation. This time R is positive, but notice they want us to move through the plane in a negative fashion because we want a point that is between negative 2 pi and 0. So that's just a full circle through the plane backwards. So what I'm going to do this time, instead of adding 2 pi, I'm going to subtract 2 pi to move in the opposite direction. They have not. All right, so we start out once again, and this is the last one of these, and then we'll move on to converting between polar and rectangular coordinates. 5 pi over 4, and I want to keep r positive, but I want to move backwards through the plane 2 pi, which we already know is 8 pi over 4. So I'm not going to show that math again. So this is pi over 4 minus 8 pi over 4. And that lands me at negative 7 pi over 4. And just to see that that's going to be the same point as if I graphed 5 and pi over 4. So here's 5 pi over 4. Okay, let me mark my polar axis. And this time it says move negative 7 pi over 4 through the plane. So here we go. Let's see. Here's negative pi over 4. Negative 2 pi over 4, negative 3 pi over 4, negative 4 pi over 4, negative 5 pi over 4, negative 6 pi over 4, and negative 7 pi over 4, and my point would land right on top of 5 pi over 4. Yes, yes, or no, no? Yes, yes. Splendid, splendid. Okay, so relations between polar and rectangular coordinates. I'm going to describe where they got these first two from so that it doesn't look like magic that all of this just happened. We know that this comes from the Pythagorean theorem there. We've used that plenty of times already in our studies this semester. And we know from previous studies that the tangent of theta is given by the ratio y over x. So how the heck did they get that x is equal to r times the cosine of theta? Well, a while ago, we picked up the information that the cosine of theta is equal to x over r. Okay, so all I have to do is multiply both sides by r here, and I end up with, well, these divide out right here, and I end up with x is equal to r times the cosine of theta. Same deal with y equals r sine of theta. The sine of theta is y over r. Multiply both sides by r, and you get y equals r sine theta. So, so that's not magic that happened like that. Welcome back, Jessica. Sorry you got kicked out. It could have to do with the weather in the area. I don't know how the weather is where you are, but we're on and off threatening bad weather here. So yeah, that's where these relations come into play. So notice we're relating r and theta, which show up as polar coordinates, with our rectangular coordinates x and y. So now we're going to be able to flip-flop between these two. And that's exactly what we're going to do for the next few slides. Okay, so here we are given the point 3 pi. Obviously, it's a polar coordinate there, or polar point, and we want to convert to rectangular point. So I know that my r is equal to 3, and I know that theta is equal to pi, and that's just from the point right there. I was told on the last page that x is equal to r cosine theta, because, you know, I'm trying to convert my r coordinate to an x coordinate, and this is how they relate to each other. And I'm told that my y coordinate relates to theta by y equals r sine theta. Okay, so there's the background information that we need to move forward. So all I'm going to do is plug in what I know. This means x is equal to 3 times the cosine of pi. The cosine is given by the x coordinate, so that's why I provided a unit circle for you here. The x coordinate at pi radians is -1. So x equals 3 times -1. X is equal to -3. So far, here's what you have found out. You found out that the x coordinate for the rectangular point is -3. Now we're going to go through the same process for the y coordinate. Y equals 3 times the sine of pi. The sine of pi is 0. So y equals 3 times 0. Y is 0. So the equivalent, this is rectangular, and this is polar. The equivalent of the polar coordinate, 3 pi, is -3, 0. Y'all okay with that? Okay. Okay, same thing here. So we'll start out by noting that r is equal to -10 and theta is equal to pi over 6. X is equal to r cosine theta. So in this case, x is equal to -10 times the cosine of pi over 6. The cosine of pi over 6 is square root 3 over 2. So x is equal to -10 times the square root of 3 over 2. I can simplify here. 2 goes into 2 once and into -10, -5 times. And I end up with x is equal to -5 square root 3. So that is the x coordinate for the rectangular point. And theta here, so I have y is equal to r times the sine of theta. Y is equal to -10 times the sine of pi over 6. Y is equal to -10. Well, the sine of pi over 6 is 1/2. I can divide out common factor of 2 from the numerator and the denominator, and I end up with a y coordinate of -5. So these are the equivalent rectangular coordinates to the polar coordinates, -10 pi over 6. Indication as to how that was for you. Okay? So yeah, I'm sure that after everything we've been through this semester, this lesson seems like pie. And no pun intended there. I'm sure it seems very easy after everything else we've studied this semester. All right, so converting a point, so we're going in the exact opposite direction. We're going to go from rectangular to polar coordinates. And the conversion process is a little bit more involved, but it's not that bad. So the first thing that you want to do in this process is to plot your point x, y. And then you have to find r by computing the distance from the origin to the point, and that's just our distance formula there. And then we find theta by using the tangent because it relates our x and our y coordinates, so the tangent of theta with the terminal side of theta passing through x and y. So we'll go ahead and take a look. Okay, so find the polar coordinates of the point whose rectangular coordinates are 1 and negative square root of 3. So the first thing I'm going to do, just like it suggested, is to plot the point 1 negative square root of 3. And the negative square root of 3 lives between -1 and -2. So 1, and so it's about somewhere around in here. And as long as you know the coordinates, the actual position of it isn't that big of a deal. But what we do need, we need to figure out what is this length from the center out to that point there. So as usual, we want to think about forming that right triangle right there. I know that's tiny, it's hard to see. But that length from the center out to the point is our length. Okay? So we've plotted the point, check. Now we want to find r by computing the distance from the origin to the point. And we were given r equals the square root of x squared plus y squared. So in this case, that's the square root of 1 squared plus negative square root 3 squared. So that's the square root of 1 plus 3, which is the square root of 4, which is 2. So r is equal to 2 in this case, which means if I'm converting to polar coordinates, which come in the form of r theta, I know that so far. All right, so now I just need to find theta, and I was told to use the tangent of theta is equal to y over x because I have y and x. So the tangent of theta is equal to, my y value is negative square root 3, and my x value is 1. So that is just the negative square root of 3. Tangent theta equals that. And now I can use the inverse tangent. So the inverse tangent of negative square root 3 has to equal theta. And when I put that into my calculator, actually I used the unit circle on this one. Let me grab a unit circle and show you how I used the unit circle here. I've got one ready to go. Hang on just a second. There we go. Let me dump it onto the page here. All right. Let's see if I can make it a little bit bigger and move it. Okay, so I am looking for some ratio of a y value over an x value that gives me negative square root of 3. So I just started looking at the unit circle, trying to pick out negative square root of 3. And I saw negative square root of 3 show up here, and I saw it show up here. Well, if I'm going to divide my y-coordinate by my x-coordinate, if I used those coordinates there, that would come out to be a positive value. So that leaves me with these coordinates here for 5 pi over 3. So let me show you how that works. If I have negative square root 3 over 2 divided by 1 over 2, that's the same thing as negative square root 3 over 2 times the reciprocal 2 over 1. My 2's divide out, and I'm left with negative square root 3. So the inverse tangent of negative square root of 3 equals theta. That means that theta has to equal 5 pi over 3. So this is 5 pi over 3. Oh, no worries, Jessica. I just saw your message that said you're slow to check because, oh, hang on, my husband just locked himself out. It won't take me 2 seconds. I'll be right back. Thank you. It wasn't my husband. It was the up sky. All right. So he wasn't locked out. He just needed to give me a package. Okay. So how was that? Was that okay? And Jessica, thank you for your dedication to joining us on your way to Florida. I hope you're not driving. You said I'm driving to Florida, so I assume you are. I'm Lizzie Gore. Thank you. Wonderful. Thank you so much. Sorry, that was the up sky again, checking my name. I guess he was supposed to check my name before he gave me my package, and he didn't. All right, back to math. Are y'all good with this? Converting from rectangular to polar? Okay, Jessica says yes, and Josh says yes. Thank y'all for your patience with me today. Okay, so converting, it looks like I have a stray theta here. Let me just scratch that out. There we go. Converting from rectangular to polar coordinates. A polar equation is, equation conversion. So now we're going to convert entire equations, not just coordinates. A polar equation is an equation whose variables are r and theta. We already know that. So there's where that stray theta was supposed to be. To convert a rectangular equation in x and y to a polar equation in r and theta, we want to replace x with, well, we already know this, r cosine theta, and we want to replace y with r sine theta. All right, so here we go. So convert the following rectangular equation to a polar equation that expresses r in terms of theta. And I'm given this linear rectangular equation, 3x minus y equals 6. So all I need to do is replace x with r cosine theta and y with r sine theta. And then you have to be a little bit clever to solve for r. So that is my first step, 3. I'm not going to write x. I'm going to multiply that by r cosine theta minus, and that is subtracting r sine theta, and that equals 6. Okay, so notice, once again, I'm trying to solve for r, and I have a factor, because this is 3 times r times the cosine of theta minus r times the cosine of theta. So I have a factor of r in both of these that I can factor out front. So if I pull an r out of both of those terms, I'm left with 3 cosine theta minus sine theta equals 6. And now, to solve for r, all I have to do is divide 3 cosine theta minus sine theta off of both sides. 3 cosine theta minus sine theta. And I end up with the polar equation, r equals 6 over 3 cosine theta minus sine theta. Now, let me explain what you're looking at. This right here, if you went and put this on the graph, started graphing a bunch of polar points that came out of it, you're going to get the exact same line that you would get by graphing 3x minus y equals 6 in the rectangular plane. Is that crazy or what? I will say, yes, that's crazy. Are y'all cool with that? Josh says yes, and we'll see if Jessica says yes. All right. Okay, so this one's a little bit more involved because you can see that we are dealing with, this is a circle, and we know that from previous studies. When we have x squared plus y squared, we're dealing with a circle. And so we're going to see how we can write the same thing in polar form. So we start the same way by just replacing x and y with r cosine theta and r sine theta. So that's what I'm going to do first. Welcome, Roy. Good to have you. R cosine theta, no worries on that. Just, I'm glad you made it. Squared plus, I'm going to replace y with r sine theta, and then that's plus 1 squared equals 1. Okay, so whenever you are raising a product to a power, that power goes to all the factors. So that first term ends up being r squared cosine squared theta. And then this next term, I'm actually gonna show you the work here just so you don't get lost. Okay, so r sine theta plus 1 squared tells me to do r sine theta plus 1 times r sine theta plus 1. And that equals 1. So for that second term, I actually need to do all of this distribution. R sine theta times r sine theta is r squared sine squared theta. R sine theta times 1 is positive r sine of theta. 1 times r sine theta is r sine theta. And 1 times 1 is positive 1. And then I have like terms right here. So I have 2 of those things. I have 2 r sine thetas. So here's where I am. I have r squared cosine squared theta, that came from that first term, plus r squared sine squared theta, plus 2r sine theta, plus r sine theta, plus 1 equals 1. Phew. Okay, now, here's another place where you have to be pretty clever. It should be sending off bells and whistles that you have a cosine squared theta and a sine squared theta sitting in there. And we know cosine squared theta plus sine squared theta equals 1. So if we can get just those 2 things added together, we can call that 1. To do that, we factor out of the first 2 terms an r squared. And that leaves us a cosine squared theta plus sine squared theta. And then I still have plus 2r sine theta plus r sine theta. I'm going to go ahead and subtract this 1 from each side. So that's going to equal 0. Were y'all cool with that stuff right there? It was kind of clever, but it shouldn't be too difficult to see. Okay, Josh says he's cool. Roy's good. Jessica, you with it? Okay, great. So this whole thing right here, everything right here, that all equals 1. So what I really have is r squared times 1 for that first term. I'm going to finish this off. I'm going to go up here. R squared times 1 is r squared. And then I'm adding 2r sine of theta plus r sine theta, and that equals 0. And hang on just a second. I lost an r sine. Oh, I'm sorry. This r sine theta is not there. I added those 2 together to get 2r sine theta. I'm so sorry. I got lost in my own handwriting there, which is not difficult to do. Okay, so we have r squared plus 2r sine theta equals 0. Now, that's it. And I know that this looks really not feeling good for you, but that is the equation. And the reason we leave it looking like that, we started out with an x squared plus a y squared. So I'm going to leave my polar equivalent of x out front, and I'm going to leave my polar equivalent of y on the left-hand side. So that's the equation in polar form. That's going to give you that circle that's centered at 0, -1 with a radius of 1. Y'all okay with that? Okay. Roy says he's all right. Josh says he's okay. I was holding my breath on that one. I was worried someone's going to be like, I have no idea what you're talking about in this score. Okay, so these next two problems that we're going to do are super quick. So we should be finishing up in no more than 10 minutes. I appreciate y'all sticking with me past 5 o'clock here. All right, so when we convert, now we're talking about going from polar to rectangular in equations. So when we convert an equation from polar to rectangular, our goal is to obtain an equation in which the variables x and y rather than r and theta. We use one or more of the following equations. So we have our Pythagorean identity there. We have the x equals r cosine theta, y equals r sine theta, and the tangent theta equals y over x. Those are the same four we used the last time. So to use these equations, sometimes it's necessary to square both sides, to use an identity, to take a tangent. So you could use a few of these to convert one equation. Okay, so here we're given the polar equation r equals 4. Yes, that's the entire equation. And we're going to try to convert it to rectangular form, which we already have the answer here. So let's see how that actually happened. Okay, so on the last page we were given the identity r squared equals x squared plus y squared. Well, we are given that r is equal to 4, which means r squared has to equal 16 because I'd have to square both sides. So I could go ahead and replace r squared with 16 and have 16 equals x squared plus y squared. That is the equation of my circle in rectangular form. Y'all don't bust a sweat on that one. That's it. That one's done. Nice, huh? Give me a green check if you're ready to move forward. Excellent. Great. Jessica, are you good? You still with us? Okay. All right, so we're going to convert the polar equation theta equals 3 pi over 4 to rectangular, which once again we've got the answer here, so we're going to see how the heck did that actually happen. Well, this right here looks a lot like my tangent ratio. So I know that the tangent of theta is equal to y over x. So that's why I started thinking of this, because I see I have 3 pi over 4. And if these were polar coordinates there, I'd have my x value here and my y value, or my r and my theta there. So the tangent of theta, which theta is 3 pi over 4, so the tangent of 3 pi over 4 has to equal y over x from there. All right, and if I want to get that x out of the denominator, because I'm trying to solve for y, oh, let me deal with the tangent of 3 pi over 4. Let me grab my unit circle again so y'all can see what it is. Okay, and I'll move this off the screen in just a second once we find the tangent of 3 pi over 4. So 3 pi over 4 lands us here. And the tangent of theta is equal to y over x. So in this case, that is square root 2 over 2 divided by negative square root 2 over 2. Well, that's something being divided by itself, positive divided by negative, so that's just negative 1. So this entire side of the equation equals negative 1. So I have negative 1 equals y over x, and I'm just trying to solve for y, because that's the form we normally write our rectangular equations in. So I'm just going to multiply both sides by x. And that leaves me with y, because those divide out, y is equal to negative x. So that is, let me move all this business out of the way. So that is equal to the negative identity line going right through the origin of the graph there. And you can see a picture of it right there. That is actually the graph of that line. And Jessica already says she's good. So, Josh, Roy, y'all doing all right? Okay. We have a couple more problems to go, and then we'll call it a day. We'll call it a semester, actually. Okay, so just a couple more equations to convert here. So we're converting the polar equation r equals negative 2 secant of theta into rectangular coordinates. So here's what I know about the secant, and this is from way back. The secant of theta is equal to 1 over the cosine of theta. So that was the first thing I kind of clued in on when I started working with this problem. So r equals negative 2. I'm not going to write secant theta. I don't want to deal with a secant. I'd rather deal with 1 over the cosine of theta. At least it's moving towards something that I know I can work with at the very least. Okay, so I can multiply, this is another little clever move here. I can multiply both sides by the cosine of theta to get that out of the denominator. Those divide out. And I'm left with r cosine theta equals negative 2. Bells and whistles should be going off in your head when you see r cosine theta, because we know r cosine theta is equal to x. So that is my equation. X equals negative 2. That is a vertical line going through the x-axis at negative 2, and you can see the picture of it off to the right there. Y'all ready for the last problem? Okay. It's a little bit of a doozy. Has completing the square in it. Jessica, you ready to move forward too, hun? All right. Okay, so I start with, oh, I forgot to put the picture of this one on there. Sorry. It's in your notes, so if you're following along in your notes, you have the picture of it right there. Okay, so we start with r equals 10 times the sine of theta. Well, I don't really have anything that helps me for r, but what I do have is that r squared is equal to x squared plus y squared. So, if I start out by multiplying both sides by r,
Jessica, did you have a question?
I get an r squared. So that's r squared. Jessica, did you have a question?
Hi.
No worries. If you'll hit your top, Thank you. It sounds like you've got a little munchkin in the car with you. I hope y'all are having safe travel. All right, so we've multiplied both sides by r, and now that right-hand side we have 10 r sine theta. Well, once again, r sine theta should be sending off bells and whistles, because r sine of theta is equal to y. So I can replace r sine theta with y. Now I have r squared is, oops, that's a squared, is equal to 10y. So I'm getting there. And I also know, let me get a different color, that r squared is equal to x squared plus y squared. Remember, I'm trying to get into rectangular form. So here I've called r squared 10y. Here I've called r squared x squared plus y squared. So I can now write 10y is equal to x squared plus y squared. Are y'all cool with that step right there? So I just took two pieces of calling r squared two different things and called them equal. Okay, good. All right, now we know that this is not proper format for an equation. I need to somehow get those y's together. So I'm going to subtract 10y off of both sides. And now I have 0 equals x squared plus y squared minus 10y. Here's where I can complete the square. I can complete the square there. And to complete the square, I add half of b squared, which is negative 5 squared, or 25. So I have to add it onto the other side as well. So plus 25 onto the other side. And here's where I am so far. 25 equals x squared plus, okay, well, let me just rewrite it first. Y squared minus 10y plus 25. So this is a perfect square trinomial, which I can rewrite as y minus 5 squared. And that's actually the equation of a circle. X squared plus y squared is a circle. And it has a radius of 5, because r squared equals x squared plus y squared. Any questions on that one? Jessica's good. Josh is good. Roy is good. Well, my friends, that is all I have for you this semester if you don't have any questions. Just as a reminder, your final exam is due Monday, May the 11th. And let me turn the recording off so people don't get confused watching this later at a later